We live at the bottom of an ocean of air. Unlike the nearly constant density of water, the density of the atmosphere varies a lot. The drawing here indicates the thinning of the atmosphere with altitude. Air density is significantly greater at sea level than above, where commercial airplanes fly. Unlike water below a well-defined surface, an exact height of the atmosphere has no real meaning. Air gets progressively thinner and thinner the higher one travels upward. Eventually, it thins out to emptiness in interplanetary space. The density of air in the atmosphere can be compared to the density of feathers in a deep pile of feathers. Blocks of feathers at the bottom are more squashed than blocks nearer the top. So it is with the atmosphere. Here's a sketch, about to scale, of a segment of planet Earth. I'll draw the atmosphere, say 99% of the atmosphere, with this blue line. We see it's very thin. For our approximately 30-kilometer thick atmosphere, it's a tiny distance compared with the almost 6,400-kilometer Earth radius. That's 1/2 of 1% of Earth's radius, akin to the thickness of skin on a common apple. So we live at the bottom of this ocean of air, which, like water in a lake, exerts pressure. The strength of the atmospheric pressure was convincingly demonstrated in 1654 by Otto von Guericke, who evacuated most of the air from a pair of sealed hemispheres. Two teams of horses couldn't pull a pair of the evacuated hemispheres apart. Here's a father and son physics professor team, Per Oluf and Johann Zetterberg, doing the same thing with a classroom pair of what are called Magdeburg hemispheres. Here's a cylinder with a piston that supports a load. When air is removed from the cylinder, there's an upward force on the piston from air outside, up against the bottom of the piston. This force is large enough to lift a heavy weight, and if the inside diameter of the cylinder is 10 centimeters or greater, a person can be suspended by this force. I ask this question: is the piston that supports the load pulled up or pushed up? I hope you didn't say pulled up, because it's common to think that the load is pulled up by a force of suction. Can a vacuum exert such a force? No, for a vacuum is an absence of matter, a condition of nothingness. So how can nothing exert a force? The hemispheres in our demonstration are not sucked together, nor is the piston holding the weight up and the cylinder sucked upward. The hemispheres and the pistons are pushed by the weight of the atmosphere. Just as water pressure is caused by the weight of water, atmospheric pressure is caused by the weight of air. We have adapted so completely to the invisible air that we don't feel it and sometimes forget that it has weight. Air is heavy if you have enough of it. If your kid sister doesn't believe that air has weight, ask her to imagine that you hand her a plastic bag of water. She'll tell you that it has weight. But if you hand her the same bag of water while she's submerged in a swimming pool, she won't feel its weight. That's because she and the bag are surrounded by water. Likewise with the air that surrounds us. The reason we don't feel the weight of air crushing against our bodies is that pressure inside our bodies balances the pressure of the surrounding air. There's no net force for us to sense. At sea level, 1 cubic meter of air has a mass of about 1.25 kilograms. So the air in your kid sister's small bedroom weighs about as much as she does. As said earlier, air density decreases with altitude. For example, at 10 kilometers, 1 cubic meter of air has a mass of about 4/10 of a kilogram, quite a bit less than at sea level. Consider the mass of air in this upright, 30-kilometer tall bamboo pole that has an inside cross-sectional area of 1 square centimeter. If the density of air inside the pole matches the density of air outside, the enclosed air has a mass of about 1 kilogram, which weighs about 10 newtons. So air pressure at the bottom of the 1 square centimeter pole would be about 10 newtons per square centimeter. Of course, the same is true without the bamboo pole. There are 10,000 square centimeters in 1 square meter, so a column of air 1 square meter in cross-section that extends up through the atmosphere has a mass of about 10,000 kilograms, which weighs about 100,000 newtons. That's 10 to the 5th newtons per square meter, or approximately 100 kilopascals. The standard international unit of pressure is the Pascal, which is 1 Newton per square meter. So 10 to the 5th pascals, roughly atmospheric pressure, is about 100 kilopascals. We write atmospheric pressure equals 10 to the 5th newtons per square meter, which can be expressed as 100 kilopascals. The average pressure at sea level is often called 1 atmosphere, abbreviated ATM. In British units, the average atmospheric pressure at sea level is 14.7 pounds per square inch. So we see that the weight of air bearing down on a 1 square meter surface at sea level is about 10 to the 5th newtons, producing an atmospheric pressure of 10 to the 5th newtons per square meter. To be more exact, the average atmospheric pressure at sea level is 101.3 kilopascals. We don't feel atmospheric pressure because pressures within our bodies balance it, just as fish deep in the ocean push outward against the huge pressures of seawater. If we remove or reduce these internal pressures, the results can be dramatic. Dan Johnson shows what happens to a gallon can when a partial vacuum occurs inside the can. Low pressure inside, not quite a vacuum, can't balance the outside atmospheric pressure. So the relatively greater atmospheric pressure on the outside crushes the can. More dramatic is evacuating air from a 50-gallon oil drum. P.O. Zetterberg uses a vacuum pump to reduce air pressure inside the drum. Barbara and Thomas Brage assist as atmospheric pressure on the outside does its thing, to the applause of the class looking on. So was the drum sucked in by the partial vacuum inside? Or was it pushed inward by the outside atmospheric pressure? Ask your friends this question. I want to leave you with a question. Atmospheric pressure against a common window produces an enormous force on the window. Why doesn't this force break the window? Until next time, good energy.